Welcome to session 2 of electronic structure theory. In this session, we'll be talking a little bit more about the properties of Slater determinants and molecular orbitals. We'll be introducing what's called the Hartree-Fock approximation, which is an approximation that describes how electrons interact with one another in what we call a mean field. That doesn't mean angry, it means average field way. In other words, each electron sort of feels the other electrons as if they were some smeared out charge distribution occupying these so-called molecular orbitals. We'll talk in more detail about Coulomb and exchange interactions. We'll introduce the concept of Koopmans' theorem, which gives a physical meaning for what does the energy of that orbital mean, and it means something about the ionization potential for removing an electron from that orbital. And I'll show you some examples of how, when we really do calculations, molecular orbitals that we obtain in these calculations are a lot more complicated looking than you see in freshman or undergraduate physical chemistry textbooks. That is, they're more delocalized throughout the molecule. And this is important because it gives us a better feeling as to why it is that when we affect one part of the molecule, the molecular orbitals then, because they touch our other parts of the molecule, they can have some effect on those other parts of the molecule. And again, we'll reinforce this problem that a single Slater determinant wave function that we talked about in session 1 isn't really a correct and accurate and absolutely correct approximation to the wave function. It's an approximation whose limitations we have to appreciate. So that's the kind of material that we'll be talking about in session 2. Okay, so this is the beginning of session 2 of our lectures on electronic structure theory. And I need to bring you back to the end of last time where we were talking about this problem that has to do with a single determinant wave function, because a lot of what I'll talk about today is related to the problems that will arise from that. And what I want to do is just to remind you that, and we talked about this olefin where we were twisting the pi bond in an olefin. And the problem was that this wave function that has two electrons, one in a pi orbital alpha, one in a pi orbital beta, that when you twist the wave function and you twist the bond there and try to express those pi orbitals in terms of like pi is left plus right over square root of 2 and pi star is left minus right over square root of 2, this particular doubly occupied orbital wave function breaks apart into something that's a 50-50 mixture of ionic, like this right-right, left-left, and covalent or diradical, right-left and left-right. And the problem is that's just wrong. We know that when we break a bond, it should break homolytically into something that has only like left-right or right-left. That is one electron on each side. We also remember from last time that you can play a trick where you could say, let's let the two orbitals be different. So you could say that the alpha electron would be in some orbital we might call pi, and the beta electron is in some orbital we might call pi prime, and this is called unrestricted framework. And when we rotate the bond, then we can break this thing apart into something where pi might, for example, evolve into left and pi prime into right. But the problem is that near the equilibrium bond length, pi and pi prime want to be the same. That is, the minimum energy is obtained when pi and pi prime are both the pi bonding orbital. And so you have this problem where as you twist the bond, you have some point at which pi and pi prime don't want to be the same. They want to evolve into left and right. And you get a discontinuity in the shape of your potential energy surface. Not in the energy itself, but in the slope. So this unrestricted Hartree-Fock or unrestricted point of view has its own problems that we have to learn how to deal with. So the bottom line is I want you to remember is anytime you have two electrons in the same orbital, like phi alpha and phi beta, and this is the case, for example, in a sigma squared, two electrons in a sigma bond, two electrons in a pi bond, and even two electrons in a pi star orbital, you're going to run into this problem where that determinant wave function will not evolve properly into the correct homolytic breakage of the bond. Now, just as a side comment, sometimes when you have a one electron bond, or a three electron bond, that is, if you have one electron in an orbital, let's say phi alpha, and let's suppose you're talking about a cation, for example, instead of the olefin. Say it was like ethylene cation with an electron removed from the pi orbital. Then in that case, you don't actually have the problem, because if it's a homonuclear case, this phi orbital, which say is the pi bonding orbital, left plus right, when you break that bond, in other words, that phi orbital will be left plus right, And phi star would be, for example, left minus right. But one electron in the orbital phi, if it is left plus right, that's still purely electron either on the left or on the right. Or let's put it a little bit more quantitatively. The wave function left plus right over square root of 2, that single determinant one electron function. If you calculate its energy, you would take that wave function, put the Hamiltonian in the middle, take the wave function again. You'll get left Hamiltonian left. That's just the energy of an electron on the left. You'll get right Hamiltonian right. That's just an electron on the right. And the cross terms will vanish because left Hamiltonian right, if these things are infinitely far apart from one another, not interacting, that cross term will vanish. So unlike the 2-electron case where you have pi, pi giving right, right, and left, left, which are the problem childs, when you have the 1-electron case, you have left or right. So it's actually okay. So 1-electron situations of this bond breaking, they don't give rise to this problem. So if you do a Hartree-Fock calculation, in other words, on a pi cation, you're okay. But if you do it on a pi squared situation, you're dead meat because of the problem. And it turns out, and I don't really have time or want to go through it at this moment, but if you have, for example, pi squared, so pi alpha, pi beta, pi star alpha, 1 electron in a pi star, it also is not a problem child. It can break apart properly, just like the cation can. But the main problem is when you have the 2 electrons in the same orbital. They're always the problem child. So just to say that one more time, what you have basically is when you take any kind of a bond and you break it by rotating it or a sigma bond by stretching it, the problem is that if you have this 2 electrons in the same orbital, this so-called restricted Hartree-Fock curve, or this curve that I'm pointing at here, is what you obtain. And it dissociates into some state that's a mixture of ionic and covalent. It's totally wrong. The correct curve is this thing I labeled full CI, which we'll learn about a little bit later on what that really means. But what happens if you try to correct this problem by letting the 2 orbitals be different, pi and pi prime, for example, so one could be left and one could be right, then what happens is that near the equilibrium bond length of your molecule, things work out okay because the phi and phi prime end up wanting to be pi and pi. But then you reach some critical bond length where all of a sudden the phi and phi prime don't want to be the same anymore to get the lowest energy. They want to evolve into left and right separately. And then you get this break in the slope of the potential curve. So this jerk, and slopes and potential curves are related to forces in dynamics. So if you're doing some classical dynamics problem, this is a disaster because you get a jerk in your forces. So this is just to remind you that these single determinant things have a lot of problems with them. Nevertheless, the single determinants, either with the orbitals restricted to be the same, like pi squared, or allowed to be the same, like pi and pi prime, where pi prime might be different than pi, this restricted or unrestricted type of thing, that forms the basis of our normal thing that we call Hartree-Fock. So I want to spend some time now talking about, even if we're stubborn and we say, I want to think that a single determinant might be a good starting point, how do I then define the best way to think of a single determinant that will make, remember there was this thing that we called the fluctuation potential that was the difference between some mean field or average potential that we're going to describe for the electrons interacting with one another, and the true 2-electron potential that was that 1 over Rij potential, the true 2-electron Coulombic interaction that made the differential equation not separable, that we couldn't really solve it. So the question now is, how can we define the best kind of 1-electron mean field potential that will give us eventually what we call Hartree-Fock theory? Now before doing that, I just need a small digression to remind you or to just tell you about whenever you have Slater determinants comprised of spin orbitals, we have to have in our heads the ability to write down the matrix element of one Slater determinant and maybe a different Slater determinant or the same one with in the middle things like appearing in the Hamiltonian operator. So these so-called Slater-Condon rules is what I want to talk about next for a little bit. So this is just a small digression analogous to atomic units. So suppose you have 2 Slater determinants that are built out of some spin orbitals. For whatever problem you have, this will always be the case. If the 2 determinants, this one and that one, are identical, now that's typical if you have determinant and you want to calculate expectation value of some operator determinant. Now the operators are always of two kinds. There's only one electron additive operators in quantum mechanics. That's like kinetic energy. Kinetic energy of electron 1 plus electron 2 plus electron 3, so forth. Nuclear traction, electron nuclear traction operators are one electron additive. Those we call F. There are other operators, and really the one that's really important to think about most of the time is the electron-electron interaction. 1 over Rij, 1 over R12, 1 over R13, 1 over R14, 1 over R23, R24, so forth. Two electron additive. That's what we call G. So the Slater-Condon rules basically say if you have two determinants that are identical, then the expectation value of any operator that's of the form F plus G, one electron additive plus two electron additive, will be, and the rule basically is sum over all the spin orbitals that appear in the determinant called phi I. So phi I, F phi I, that's just the expectation value of whatever the F one electron operator is for spin orbital I. That sort of makes sense. It's just saying sum over all the spin orbitals of their own expectation values of the F operator. And then for the two electron operator G, the rule is you sum over all pairs of spin orbitals. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. That's what this I greater than J counting here would be. And then you take this two electron integral, it's called, phi I for electron 1, phi J for electron 2. G12, you know, if G is 1 over R12, then that would be 1 over R12. Then phi I for electron 1, phi J for electron 2, minus phi I for electron 1, phi J for electron 2, G12, phi J for electron 1, phi I for electron 2. That's a so-called exchange term. So the general idea is you sum over all the one electron expectation values for every spin orbital that's in your determinant, and then you sum over all of these so-called direct and exchange. And if this G happens to be 1 over R12, we call it the Coulomb and exchange operator interactions between spin orbitals I and J. Now I should mention one thing. This sum over I greater than J that I mentioned before, 1, 2, 1, 3, 1, 4, 2, 3, 3, 4, sometimes that's written as 1/2 the summation over I not equal to J. And it's exactly the same thing, because in that terms it would be 1, 2, 1, 3, 1, 4, 2, 3, 3, 4, 2, 1, 3, 1, 3, 2. It would have the same terms in there double counted, so you just divide by 1/2. Okay. Now the other two Slater-Condon rules basically are what if you have two determinants that differ by a single spin orbital? Now this arises when you are doing spectroscopy, where you say I have some wave function that describes my molecule, then I have a different Slater determinant in which one spin orbital has been excited from some orbital to another orbital. And let's suppose that the orbital out of which you have excited is called phi p prime, and the orbital into which you've excited is called phi p. So they differ only by phi p and phi p prime. That's your excitation, let's say, in spectroscopy. So if you have to calculate now the matrix element of any 1 and 2 electron operator, now you could ask me, well, Jack, what if you have a problem where there's only a 1 electron operator in the middle? Okay, then just put G equal to 0 and use only the F part of these rules. So anyway, say you have a determinant where they differ by 1 spin orbital. What's the formula for the matrix elements? Then what it is just take the 2 spin orbitals by which they differ, phi p prime and phi p, and put the 1 electron operator in the middle. It would be electric dipole operator in spectroscopy, and calculate that integral. And then add to that, if the matrix element you want to evaluate contains some 2 electron operator too, like the Hamiltonian, the summation over all the spin orbitals that are common to both determinants, that's labeled J, then it'd be phi p for electron 1, phi j for electron 2. G of 1, 2, phi p prime for electron 1, phi j of electron 2, minus an exchange part. Then the third Slater-Condon rule. I know that probably you had these as students, but I'm more or less saying they're so important we need to remind ourselves and more or less memorize them, Diane, eventually. No, he wants me to do this. What if you have 2 determinants that differ by 2 spin orbitals? Now this will be the case when we're actually doing perturbation theory, what's called Møller-Plesset perturbation theory, which we'll get to in a couple more sessions. So suppose you had, for example, an olefin that had 2 electrons in a pi orbital, so pi squared, and then we had another determinant that was pi star squared, and we wanted to calculate something about the Hamiltonian matrix element between those 2 determinants. They differ by 2 spin orbitals, pi alpha, pi beta, pi star alpha, pi star beta. Well, in that case, what you do is you say, first of all, there's no contribution from the 1 electron part. That is, these 2 determinants that differ by 2 spin orbitals, if you have a 1 electron operator in the middle, their matrix element is 0. But if there's a 2 electron operator in the middle of any form, then the formula basically is just take the 2 orbitals that appear in the 1 determinant that don't appear in the other, and so you, for example, you put phi p for electron 1, phi q for electron 2, g of electrons 1 and 2, phi p prime of electron 1, phi q prime of electron 2, minus the exchange one. Then final matrix element is, what if you have this determinant and this determinant, and they differ by 3 or 4 or 7 or anything 3 or greater? Then the matrix elements of any 1 and 2 electron additive thing is 0. Then the final thing, just to mention parenthetically, is if we have the identity operator. So suppose in the middle here we don't have 1 electron kinetic energy or 2 electron, 1 over R1, 2, but we just have the identity operator. So for some reason, we have a reason to say, what's this determinant and this determinant integrated against one another with just 1 in the middle? The answer to that is it's 0 unless the 2 determinants are exactly equal to one another. Okay, so those are the Slater-Condon rules, which more or less we all should have committed to memory eventually. Okay, now let's return to this physical problem of how does one define a good mean field potential? And let me remind you the reason you want to do that. In the electronic Schrodinger equation, we have the kinetic energy of the electrons, which is 1 electron additive. We have the electron nuclear attraction Coulomb term, which is 1 electron additive. If that's all we had, then the whole Hamiltonian would be 1 electron additive. So the wave function of that Hamiltonian could be taken as a product of 1 electron terms for electron 1 times electron 2 times electron 3. But we're dead meat, because the real Hamiltonian has also this 1 over R1, 2, 1 over R1, 3, etc., pairwise additive terms in there that make the Schrodinger differential equation not separable. So what we do is we say, I wonder if you could replace that true electron-electron interaction by some model interaction we call mean field interaction that is additive, 1 electron at a time. That's the reason we're motivated to do this. Because if we can, then the solutions of that Hamiltonian with the approximate interaction there are going to be products of functions 1 electron at a time. That's where the Slater determinant concept came from. So what do we do? Well, the first thing we do is to say, what if we think of a Slater determinant, because we know that's the kind of function that will arise if we have a 1 electron additive potential. So if we take a Slater determinant and we write down using the Slater-Condon rules its expectation value, Slater determinant, Hamiltonian, Slater determinant, just to sort of see what are the various terms that we would see that would arise in the energy of such a function. The Slater-Condon rules tell us, well, we would have a sum over all of the spin orbitals that are appearing in that Slater determinant, that's what I mean by K occupied, OCC, of the kinetic energy, electron nuclear attraction, and nuclear repulsion operators. Those are the F-type terms that were in the preceding thing I talked about in generality. So just the kinetic energy, nuclear attraction, and nuclear repulsion energies sandwiched between each spin orbital that's occupied in there. So that just says add up the contributions of your 1s alpha, 1s beta, 2s alpha, 2s beta, 2px alpha, 2py alpha, if you're a carbon atom, of the kinetic energies and nuclear attractions and so forth. But then the next thing it has is it says, please now sum over all the pairwise interactions between electrons. Now this, I write it here now as this 1/2 K not equal to L, just to remind you that could be K less than L, or a half K not equal to L. So this just says, please add up all of the Coulomb minus exchange interactions among the spin orbitals that are in your determinant. So this is just Slater-Condon rule applied to a single determinant with the particular case of the electronic Hamiltonian with its kinetic, electron nuclear Coulomb energy, and electron-electron repulsion energy, the E squared over R12 terms. And these E squared over R12 integrals that I'm pointing at here, we call the Coulomb integrals, and these that I'm pointing at here, we call the exchange integrals. Okay, now the idea of Hartree-Fock theory is the following. That's the formula for the energy of any Slater determinant. But now the question is there a way we could have chosen these spin orbitals, these phi's, so that they give the minimum value of that energy? So we do a derivation where we say, let's vary this energy with respect to these orbitals and ask which orbitals make that energy minimum. Now there's some constraints we have to place on these orbitals because we want these orbitals to be orthonormal. So we put constraints on the minimization process where the integral of phi j, phi k against one another is equal to 1 if phi, it just means normalized, and if phi k is not equal to phi j, then we say 0. So that's our way of saying that we want those orbitals to be orthonormal. Why did we want them to be? Because our whole concept of the Slater determinant and then these Slater-Condon rules were predicated on the assumption that the orbitals were orthonormal. The Slater-Condon rules we just wrote down wouldn't be valid if the orbitals weren't orthonormal. So what we do is we go through a derivation, we minimize the energy. That gives us a set of equations that the optimal, that is the best phi's, obey. And those equations are called the Hartree-Fock equations. We generally write them as little h phi j equal epsilon j phi j. But H contains kinetic energy, electron-nuclear attraction potential, nuclear-nuclear repulsion potential, then acting on phi j. But H also contains these so-called Coulomb minus exchange potentials or operators. And I'm going to go into more detail in the next slide about them in a minute. But let me make one parenthetical comment here about this. We say that we minimize the energy with respect to these orbitals. That's not quite true. We have a function here that is a function of these orbitals, and you can see it's quadratic. See, here's phi j, phi k, and phi k. So the function is quadratic in these unknown functions, phi's, but it's also quartic. See, phi phi, phi phi, phi phi, phi phi. So we have this function here that in principle is a quartic functional, we call it, because it's a function of functions, the functions being our orbitals, the functional being the energy functional. We have this thing that we have taken the first derivative of with respect to the orbitals and set equal to 0 to get the Hartree-Fock equations. When you have a function and you take its first derivative and set it equal to 0, you're not necessarily guaranteed you're going to get the minimum. You could get a maximum, you could get an inflection point. So Hartree-Fock theory really is based upon making the energy stationary. The reason I go through that rigmarole is that when we do Hartree-Fock calculations, sometimes the process we go through when we do these things converges to things that are not the true minimum. That is, some excited states are sometimes coming into the problem. And sometimes we even have trouble where we want to converge to an excited state and the thing collapses to a lower energy state. So controlling which local minimum the energy surface, the energy converges to when we do Hartree-Fock theory is a problem because our whole Hartree-Fock equations are predicated on finding just stationary points, that is, minima, maxima, or inflection points. But nevertheless, we think of doing Hartree-Fock theory to get the minimum energy. So physically what we're trying to do is to say, can we make a choice of these spin orbitals to give the lowest energy being defined as the expectation value of that Hamiltonian? Now, I want to give you a little bit of a picture physically about what are these doggone Coulomb and exchange potentials that arise here. In the preceding transparency that I'm back to now, what I'm talking about here is this Hartree-Fock equation, H operator phi j equals epsilon j, orbital energy, phi j. In the H operator, there's this complicated looking Coulomb minus exchange junk here. And what I want to just talk about is what does that physically mean? Well, a Coulomb integral, for example, J12 that's sitting here, physically it means, well, mathematically it means take the integral of phi 1 squared for electron 1, let's say, or here I just called it electron r. Now squared, of course, means phi 1 star phi 1, complex conjugate times itself. And then take e squared over r minus r prime. R and r prime are the positions of the two electrons. And then take phi 2 of r prime squared. Now physically this means I'm an electron r, and Monica is an electron r prime. E squared over r minus r prime, the distance between these two, the two of us being r and r prime, is our Coulombic interaction. Phi 1 squared is sort of the probability cloud, the probability density of finding me at some point r in space. So if I'm an electron that's in that spin orbital phi 1, then phi 1 squared of r gives the probability density. So for example, if this p orbital here is the orbital in which I, the electron r, resides, then the square of this cloud is the probability density in space of finding me at various points in space. Phi 2 r of r prime squared, with Monica being r prime, let's say phi 2 is this s orbital here. Then the square of that cloud is the probability density for finding her at various places. So the physical meaning of this just means, please sum over all places r and sum over all places r prime, integrate, and take the probability of finding me at point r times the probability of finding Monica at point r prime times e squared over r minus r prime, our instantaneous interaction. So it's our averaged out over these probabilities Coulombic potential of interaction between us. That's what that is. Now, sometimes when we write that integral down, what we do is to think of it as being, for example, here, phi 2 of r prime squared is Monica's probability density. If we think of the rest of the integral, phi 1 of r, e squared over r minus r prime, integrated over r, if we think of that as J1 of r, that's what the Coulomb potential is. So J1 of r is take me, take e squared over my distance from me to Monica, and average over me, that is average over r, the position of me, that's electron r, and that gives the average Coulombic potential that Monica feels due to me. So there's two different things we have, the total interaction potential averaged and the average potential that I present to Monica. But of course there's the opposite point of view. I could think of myself as being special, phi 1 of r squared, and I'm here, and I take Monica and I average out over her motion, and that gives the potential J2 of r. That's the potential she exerts on me. So these Coulomb and exchange potentials and Coulomb and exchange integrals have physical meanings like that. One of the things that you ought to keep in mind, though, just prejudicially, is that generally Coulomb integrals are bigger than exchange integrals. The reason is the following. See, in an exchange integral, for example, between me and Monica, the way an exchange integral reads is we take phi 1 of r times phi 2 of r. Now that phi 1 times phi 2 is only non-zero in the region where orbitals 1, phi 1 and phi 2 are touching, that is, have overlap. Then we take phi 2 of r prime and phi 1 of r prime. That also is the product that's only non-zero in the overlap region. And then we take e squared over r minus r prime. So the exchange integrals really, they die off exponentially with the distance between orbitals because the overlap between orbitals, the overlap region there dies off exponentially with distances. Whereas Coulomb integrals, even if this orbital and that orbital aren't touching one another, we still have an electrostatic Coulomb interaction between an electron in this charge density interacting with an electron in that spherical charge density, even when they're like 10 angstroms away. They don't have to be touching because there's still this Coulombic potential between them. So Coulomb integrals are long range. Exchange integrals tend to die off exponentially with distance. Okay, so that's just a little bit of a physical picture of what are Coulomb and exchange things. Okay, so let's go back now, and I want to talk a little bit more about the implications of making this particular definition of the mean field potential. Because, so what is the definition? Well, the idea is that by doing this Hartree-Fock derivation, we end up with a one-electron Hamiltonian that these optimal orbitals obey. And it is kinetic energy, it's electron-nuclear attraction, nuclear-nuclear repulsion, and then the mean field potential, the VMF, as we're calling it, that Hartree-Fock theory defines is this sum of Coulomb minus exchange potentials. J minus K is Hartree-Fock's definition of the mean field potential. Okay, now we want to talk about that. Is it good? Is it bad? Is it ugly? What are its strengths? What are its weaknesses? So that's the definition of Hartree-Fock's mean field potential. One of the implications of Hartree-Fock's definition is that if we think about doing perturbation theory, that is, if we said that we have a real Hamiltonian that's kinetic energy, nuclear attraction, nuclear repulsion, plus the true E squared over Rij's, that's H. And we're going to say that H0 we're going to take according to the Hartree-Fock definition, where it's H0 is kinetic energy, nuclear attraction, nuclear repulsion, and we're going to replace the electron-electron repulsion by J minus K. That's H0. If we make that mentality, and then we say we're going to do perturbation theory, where the difference between H and H0 we're going to treat as a perturbation. Then in perturbation theory, one of the things we do is we say, well, the energy is equal to the 0th order energy, which would be psi times H0 times psi, and then we calculate the first order correction to that energy by taking the psi 0 perturbation psi 0. And when we do that, the H minus H0 is the perturbation, and that's the electron-electron repulsion minus the J minus K. And to calculate, therefore, the first order energy in Hartree-Fock theory, we would take our Slater determinant. In the middle, we would put H minus H0. On the right, we put our Slater determinant. And the problem now is that, not the problem, but the good news, is that vanishes. The first order energy correction vanishes. Why? Because Slater determinant V electron-electron Slater determinant ends up being essentially just the sum of the Coulomb minus exchange potentials. And that's what Hartree-Fock theory has as its replacement for the electron-electron repulsion. So the bottom line, just to say it physically, is because Hartree-Fock replaces VEE by J minus K, then the average value of VEE and the average value of J minus K end up being identical. And that makes it so that in Hartree-Fock theory, the first order correction to the energy vanishes. And you say, well, that's good because it means maybe the theories converged. No, because the second order, third order, fourth order, and fifth order don't vanish. But that's just one of the observations about Hartree-Fock theory, is there's no first order correction to the energy. So when we do what's called Møller-Plesset perturbation theory, MPN, what it is it says, Møller-Plesset perturbation theory says the H0 is the Hartree-Fock definition of the problem. The perturbation then is the true electron-electron repulsion minus Hartree-Fock. You take that as your perturbation. Then you just apply normal textbook perturbation theory to that starting point, and that gives a series of energies, E0, E1, which is 0, E2, E3, so forth. And those are the so-called MPN energies. We'll talk about that later. Okay, now I just want to hammer one other thing here. When you're teaching chemistry to young students, we all talk about these orbitals and spin orbitals and stuff like that. In real rigorous theory, where we started out with the full n-electron Schrödinger equation and the nuclei moving and all that, we made the Born-Oppenheimer separation. That gave us an electronic Hamiltonian, an electronic problem to solve. That electronic problem has a non-separable component to it, 1 over Rij. Killed us, made it so that we could not separate the differential equation. But once we introduce a model for the 1 over Rij's in this mean field sense, that is the step where we are allowed to say, okay, within that model, if the electron-electron interactions are replaced by these one-electron additive Coulomb minus exchange things, that's what allows us to say that within that model, the wave function would be a product of spin orbitals, one for each electron. So orbitals arise because of the Hartree-Fock type model, the mean field model. Okay, now I want to talk about some good, bad, and uglies with respect to these orbitals. And I think most of these you've had in classes, so I'm just going to repeat them here, but try to give you some physical insight to them. One thing is, if you make the particular choice of the Hartree-Fock orbitals, that is the ones that minimize the energy, they gave rise to that particular choice that the mean field potential was the J's minus K's, then those are Hartree-Fock orbitals. Their orbital energies, that we call epsilons, we usually have them gathered into the ones that, the orbital energies of the spin orbitals that appear in our Slater determinant, and then the Hartree-Fock orbital energies that don't appear in our Slater determinant. Now you say, wait a minute, how did those ever arise? Well, if you look back at the Hartree-Fock equations, they say H phi k equals epsilon k phi k. And H was kinetic energy, nuclear electron nuclear attraction, nuclear repulsion, and J minus K. But that H that kinetic energy operator there is a differential operator, second order. That's a differential equation. It's Hermitian. It has an infinite number of solutions. Some of them, the phi k's, correspond to those that you place into your Slater determinant. We call them the occupied spin orbitals. But there's more solutions to this Hermitian Hamiltonian in the complete set. There's these solutions that don't appear in your Slater determinant that define the Coulomb exchange potentials. We call them virtual or unoccupied orbitals. So they exist also. Now, in what's called Koopmans' theorem, as our friend Vince would say, or I say Koopmans' theorem, most people say Koopmans' theorem, the idea is the following. You have a set of spin orbitals that appeared in your Slater determinant. Let's call the Slater determinant psi 0, and phi 1 through phi n appeared in there. If you were to take, for example, and add, without changing the orbitals, you get the orbitals from a Hartree-Fock calculation on your problem that contains n electrons, say it's ethylene molecule. And then you were to take and add an electron to the, for example, n plus first orbital. Doesn't have to be n plus first, it could be n plus eighth, but some so-called virtual orbital. And form a Slater determinant that I call psi minus, that is the same psi as you started with, but with one more electron added to some previously unoccupied orbital. If you then do the following derivation, you write down using the Slater-Condon rules the energy of this psi 0. That would already be written down. It's the Hartree-Fock energy. Then you take the Slater determinant psi minus and write down that n plus 1 electron determinant here, n plus 1 electron determinant here, Hamiltonian. When you do that, using the Slater-Condon rules, which I've just repeated for you here, you take those two expressions and subtract them. The reason is you're trying to calculate an electron affinity, or an energy difference, between the n and n plus 1 electron Slater determinant. That energy difference you get that I've written here, delta E, ends up being the following. You end up with one extra kinetic energy, an electron nuclear and nuclear repulsion integral. That's not surprising because there's one more term in this n plus 1 electron determinant than there was in the n electron. So when we write the Slater-Condon rules for that F part, the 1 electron integral part, you would have one electron integral in the bigger determinant than you had in the small determinant. Then the other terms are a little bit more complicated because in the n plus 1 electron determinant, you had Coulomb and exchange energies of interaction of that n plus first electron with all the other electrons. But in the n electron determinant, you didn't have those terms there because the n plus first electron wasn't there. So what you end up with is also the summation over L, L being all the spin orbitals that are appearing in both determinants of phi n plus 1, phi L, phi n plus 1, phi L. So that's just a Coulomb interaction of the electron in the n plus first determinant or orbital with the other orbitals minus the exchange interaction of that n plus first electron with the other electrons. And it turns out when you go through this derivation of the energy of these two determinants, write it down, that's what you get. But then if you go back to the expression for what is the expression for the energy of the n plus first orbital, it turns out, you have to go back to your Hartree-Fock equations to do this, it turns out this doggone thing here is exactly the same as the energy of that n plus first spin orbital. So the derivation basically says that the energy difference between an ethylene and an ethylene anion, where you've added an electron to a previously unoccupied orbital, is equal to the energy of that previously unoccupied orbital. That's not surprising, but unless you use the Hartree-Fock orbitals, this whole derivation wouldn't be true. So it's only because the Hartree-Fock definition of the mean field potential was used that you get this well-known, chemically taught at the freshman level identity. So Hartree-Fock orbitals are the ones that you can use to approximate, at least, in this case, electron affinities. If you did a derivation where instead of using a Slater determinant with one fewer electrons, you took your original Slater determinant and you removed, say, spin orbital n or spin orbital 3 or any of the previously occupied ones, a derivation like this could be gone through, and the energy difference would then end up being the energy of that previously occupied spin orbital. So just what we're saying here, and this is what I repeat up here, is that if you do the derivation for an occupied orbital, You have an n and an n minus 1 electron determinant. You go through your derivation. Energy difference is the energy of the occupied orbital. Now, so fact number one is that in Hartree-Fock theory, the energies of the occupied orbitals give us approximations. Now, why are they approximations? Because Hartree-Fock theory is an approximation. It's not exact. And also, when we do this derivation, we said, let's take the orbitals of ethylene, and let's place an electron into a previously unoccupied orbital, but let's not let the orbitals change at all, to relax, to adjust to the presence of that electron. That's the derivation we did. When we remove an electron from an orbital to do ionization potentials, we do likewise. We say, let's remove an electron, but let's use the same orbitals as was for the ethylene. So we made various approximations, Hartree-Fock and frozen orbitals. So within those approximations, though, the Koopmans theorem says that the occupied orbital energies tell us ionization potentials. The virtual orbital energies tell us electron affinities within these approximations. That's one of the good things about Hartree-Fock theory. Its orbitals have those characteristics to it. But there's another thing I'd like you to sort of focus on here on this slide. If we look carefully at the energy expressions in here for the occupied orbital energy, you'll see that in the case of the occupied orbital energy, let's say it's the nth orbital. The particular term in this sum where L runs over the occupied spin orbitals. The term L equals that particular orbital here I'm calling O. Maybe it's the last orbital of my molecule, the last occupied. We would have phi O, phi O, phi O, phi O. It's off to work we go. Then we'd have minus phi O, phi O, phi O, phi O. So what I'm saying here with this little joke is that in the case of occupied orbitals, the Coulomb interaction of that occupied orbital with itself, the so-called self-interaction. Now that's something that's going to come back and we'll hear when we talk about density functional theory much later in these series, that there's something wrong in density functional theory with the so-called self-interaction. But in the case of these Hartree-Fock orbitals, I just want you to notice that in the energy expression for the energy of an occupied orbital, the so-called self-interaction, the Coulomb integral of the orbital with itself minus the exchange interaction of the orbital with itself, they perfectly cancel. They're exactly canceled out, which is correct. Electrons don't feel themselves. So in the case of occupied orbitals, then we say the orbital energy expresses its kinetic energy, its electron nuclear attraction, and its interaction with the other electrons, with the n-1 other electrons. Now I want to go back and look at the same kind of expression that we had on the preceding transparency, or preceding slide, for the energy of one of the virtual orbitals. If I were to look back at that preceding thing, we would see that the energy expression we had for an unoccupied orbital was its kinetic energy and nuclear attraction, and then we have a summation over L running 1 through n, the occupied spin orbitals, and here I'd have phi unoccupied, phi L, phi unoccupied, phi L, minus the exchange. Notice that there is no term where L equals the unoccupied guy. So in this case, the unoccupied spin orbital phi u that's sitting here feels n. It feels interactions with n electrons. The occupied spin orbital that I'm pointing to here, that we talked about a minute ago, felt interactions with n-1 because its interaction with itself canceled out. So there's a qualitative difference about the energy content, the physical meaning of these orbital energies. An occupied orbital energy means the kinetic energy, nuclear attraction potential pulling on that orbital, and that orbital's interaction with n-1 other guys. The virtual orbital energies are the kinetic energies, electron nuclear attraction potentials, and an electron in that virtual orbital's energies of interactions with all n electrons in the neutral molecule. So there's a difference. These guys feel n electrons repelling them. The occupied guys feel only n-1 electrons repelling them. Now that's really important because virtual orbitals in Hartree-Fock then tend to be much more diffuse. So let's just take ethylene as a concrete example. If I'm a closed shell ethylene molecule, I think all of us would say the HOMO, the highest occupied orbital, is probably our pi orbital. And then we have maybe our carbon-carbon sigma and our carbon-hydrogen sigma These are our occupied orbitals. The pi orbital, an electron in a pi orbital feels the carbon nuclei, the protons in the molecule, the other electrons. It feels all the electrons in the molecule except itself. The pi star orbital, though, feels the nuclei pulling at it. It feels all the electrons, including the two that are in the pi bond. So it feels one more repulsion than the pi orbitals do, because the one electron that's in the pi orbital, let's say beta, feels the pi alpha electron, but it doesn't feel itself. So the pi orbitals will be more compact, whereas the pi star orbitals will be more diffuse because they have more repulsion, more electron repulsions. Okay, so this is just repeating this thing. If we limit ourselves to the Hartree-Fock picture, Koopmans theorem, the unoccupied orbitals give us approximations at least to electron affinities. Occupied orbitals, approximations to ionization potentials. But, and this is one of the mistakes that many of my chemist friends make, another problem with the orbital energies is you might think that if we take the energy of an occupied orbital and the energy of an unoccupied orbital and we subtract the two, that'd be a pretty good approximation to, let's say, a excitation energy of the molecule. Wrong. Why? Because in an excitation, let's say in the case of ethylene again, if we go back to that, an excitation energy would take an electron out of the pi orbital. Okay, now that you might say that's in Koopmans' theorem, that's the energy of that pi orbital, the amount of energy necessary to take it out. That's right. But then when you put the electron, say, into the pi star orbital of the excited state of ethylene, that pi star orbital for the excited state of ethylene looks down and it no longer feels two electrons in the pi orbital. It feels only the one that was left behind. So excited state pi star orbitals are really more compact. The Koopmans theorem virtual orbital would be more appropriate for ethylene anion, an electron in a pi star orbital with a neutral ethylene still existing down here. That's what the virtual orbital of ethylene is at Koopmans' theorem. The kind of orbital you need if you want to look for excitations is the occupied orbitals are okay, but you need to use virtual orbitals that correspond to the cation. So you'd want to do a calculation, say, on the ethylene cation, and then look at its pi star orbital, because that would have a vacancy down here in the pi orbital. So the virtual minus occupied orbitals that you obtain from just the virtual Hartree-Fock orbitals, occupied Hartree-Fock orbitals, never use those as approximations to excitation energies, because the virtual orbitals feel too many electrons. They're too diffuse. Okay, now there's another thing. When you take these Hartree-Fock orbitals and you say, I think that it makes sense to add up the energies of all the occupied spin orbitals. That should be the energy, right? Well, that's not quite right. Because what we know is if we take a Slater determinant, Hamiltonian Slater determinant, and write down the energy, as I've done here again for you, we get our friendly Slater-Condon rules, summation over all the occupied orbitals of their kinetic energy and nuclear attraction, etc. Then we get our friend, the 1/2 k, or not equal to L, or if you want, k greater than L, of the Coulomb minus exchange interactions. That's the Hartree-Fock energy. If you go back to the expression for the orbital energies, the epsilon k's, the orbital energies were kinetic energy, nuclear attraction, and Coulomb interaction of the nuclei with one another, expectation value for each spin orbital. And then each orbital's energy involved its interaction with all the other occupied orbitals. So the problem is if you take those Hartree-Fock orbital energy expressions and add them up, you do get the same sum of kinetic energies and nuclear attractions as you do out of the Slater-Condon rules, but the problem is that the Coulomb minus exchange interactions are double counted. That is, if you take the summation of all the epsilon k's, you would have a summation over k, and then for each of those epsilon k's, you would have its interaction with the other spin orbitals there. So just as a concrete example, say you had 3 spin orbitals. The energy of the expression for the energy of orbital 1 would involve its Coulomb interaction with orbitals 2 and 3. So we'd have a J12, J13, minus the k's also. The energy expression for the energy of orbital 2 would have its J21, J23 in there. And the energy of expression for orbital 3 would have J31 and J32 in there, minus their exchange. So if we take the energies and add them up, we sort of will double count. We'll have J12 and J13, and then in her energy, she'll have J21 and J23, and in hers, it'll be J31 and 32, and you'll double count. So the summation of the Hartree-Fock orbital energies double counts the Coulomb repulsions and the exchange interactions. So the bottom line is the sum of orbital energies is not the total Hartree-Fock energy of your molecule. You never want to do that. And the programs we use don't do that. But sometimes our friends in chemistry want to do that. And they don't mean that, because they have a double counting of the Coulombic interactions. Now, another thing, just for pedagogical purposes here, when we look at these orbitals in textbooks, when you look at an ethylene molecule in a textbook and look at the pi orbital, you see this nice plus minus, looks nice. The orbitals in Hartree-Fock theory, the real orbitals that you get out, are actually more spread out all over space than you might expect when you're based upon your introductory freshman chemistry experience. And I just want to show a couple of these things here. So here is a molecule that contains a sugar and a phosphate and a sugar, just a phosphate group that has two sugar molecules attached to its so-called 3' and 5' sides. And the bottom line is, all I want you to notice is, for example, on the phosphate group, we have a phosphorus double bond O to one of the things, and then you have the PO groups that form bonds with the sugars. But the PO double bond O has a pi star orbital, and here it is. And that orbital, when you look at it, you say, boy, it's sort of messed up. It's not just on the phosphorus and the oxygen. It seems to have little parts that go out and touch the other parts of the molecule around it. That's true. The Hartree-Fock orbitals they tend to be fairly delocalized. They're somewhat difficult to identify as being only representative and only touching the particular bond that you are thinking that they should touch. Part of this derives from the fact that the orbitals have to be orthonormal to one another. That is, if I have a bond here between a carbon and oxygen, and I have a Hartree-Fock orbital that's this CO sigma orbital, it has to still be orthogonal to all the other orbitals in my molecule. And to be orthogonal, it has to have little pieces in those regions of space to have plus and minus signs to give zero when I integrate the orbitals against one another. So Hartree-Fock orbitals, when we really see them in reality out of a computer output, are actually a lot more complicated and scarier, if you will, than we are used to. But that's the way they are. Now, another attribute of Hartree-Fock orbitals, we are winding down here in this discussion of this particular session, in case you're getting tired, but I just want to make sure we go through some of the strengths and weaknesses of Hartree-Fock point of view. Another attribute of Hartree-Fock, the particular Hartree-Fock definition of the so-called mean field potential, is something called the Brillouin theorem. Now, some guy named Brillouin came up with this, but the basic idea is that when we start to do perturbation theory, like I talked about, we're going to say our zeroth order picture is Hartree-Fock. So we have a single determinant wave function that's our zeroth order wave function. I already talked about the fact that when we apply perturbation theory, we take that wave function, and in the middle we put our perturbation, which is the true electron-electron interaction minus our Hartree-Fock definition of it, J minus K. And one of the attributes of Hartree-Fock theory is that matrix element ends up being zero. There's no first-order energy correction in Hartree-Fock theory. But another thing that you might remember from perturbation theory is you have corrections to the wave function too. We have a wave function that's our zeroth order Slater determinant, Hartree-Fock. We want to now say, what is the first order, second order, third order correction to it? Well, the way that we do that when we do Møller-Plesset perturbation theory derivation, we'll talk more about it later, is we say the first order wave function is in principle expressible as a linear combination of Slater determinants, because Slater determinants form a complete set. Why? Because they're comprised of spin orbitals that came from a Hermitian operator that formed a complete set of spin orbitals. So what we do then is this first order wave function, we express it in terms of other Slater determinants. So we have our reference Slater determinant, our Hartree-Fock. For ethylene it would be 1s squared, and then all these bonds doubly occupied, and the sigma bond doubly occupied, and the pi bond doubly occupied. We express our first order wave function also as determinants, but so-called excited determinants that differ from the one we start with by 1 orbital, or 2 orbital, or 3 orbital, or 4 orbital excitations. And the Brillouin theorem just says that when we do our perturbation theory, one of the ways that we evaluate these first-order wave function is we have formulas in perturbation theory that say psi 0 perturbation and then some excited determinant. And when we do those evaluations of the one determinant Hamiltonian, another determinant, we have to use our Slater-Condon rule. So we're talking about, here's our reference Hartree-Fock determinant. Here's a determinant that differs by one excitation, let's say, because we're trying to evaluate that matrix element. And when we go through that, where we have promoted, for example, spin orbital A to spin orbital M, so that might be like pi to pi star, or it might be carbon-oxygen sigma, well, in the case of a formaldehyde. In the case of this ethylene, it might be carbon-carbon sigma to pi star, but any kind of single electron excitation. When we go through that, our Slater-Condon rule says, well, the rule is take orbital phi A, take orbital phi M, put in the middle the F part of our operator. And then take orbital phi A and phi M, phi A and phi M, and put the J minus K in the middle. And when we do that, we say, oh, wait a minute. This kinetic energy, electron nuclear and nuclear nuclear, plus this summation over L of phi L, phi L, phi L, phi L, that's just the Hartree-Fock operator. That's the Hartree-Fock Hamiltonian. Kinetic energy, electron nuclear, J minus K. So this ends up being just phi A, Hartree-Fock operator, phi M. Then we say, whoa, wait a minute. Hartree-Fock operator acting on phi M gives epsilon M, phi M. And then phi M and phi A are orthonormal, so we get 0. And that's right. Within Hartree-Fock theory, the matrix element of the Hamiltonian between your Hartree-Fock determinant, any determinant that's singly excited, ends up being 0. The importance of this is when we do perturbation theory, our corrected wave function, our 0th order wave function is Hartree-Fock. Our corrections then involve maybe single excitations, double excitations, triple excitations, etc. And this theorem says the first order wave function doesn't involve any single excitations because the matrix element of Hartree-Fock perturbation, single excitation, is 0. So the Brillouin theorem is one way that we basically prove that in Hartree-Fock theory, the nice thing is the singly excited determinants don't contribute to the wave function in first order. Okay, now we're sort of coming toward the end of this now. I want to come back to this idea of determinants, configurations, configuration state functions, when we're in trouble and when we're not in trouble. Now, first of all, configuration, just to repeat a little bit of jargon here. At our undergraduate level, configuration just means 1s squared, 2s squared, 2p squared, carbon atom. Okay, that's true. That's a configuration. In case of ethylene, it might be all the orbitals doubly occupied and then pi squared for our last two orbitals. That's a ground configuration of ethylene. Another configuration might be 1s squared, 2s squared, 2p1, 3s1 for carbon atom. Excited configuration of carbon. For ethylene, all the orbitals doubly occupied, pi alpha, pi star alpha. That would be an excited state configuration of ethylene. But configuration state functions, what they are is, once I tell you a configuration, what is the minimum set of determinants that I must write down to be consistent with that particular configuration? So for example, in the case of the carbon atom, if I were to say to you 1s squared, 2s squared, 2p squared, and I want you to write down triplet p carbon, because that configuration has triplet p, singlet d, and singlet s. Well, for the triplet p state of carbon, a Slater determinant's 1s alpha, 1s beta, 2s alpha, 2s beta, 2px alpha, 2py alpha. That determinant, you can prove, has triplet spin character, alpha alpha, and it does have L equals 1, the p character to it. So that particular Slater determinant would be an acceptable configuration state. See, state is the triplet p, or singlet d, or singlet s. So configuration state function. So in the case of carbon, for that particular state of carbon, we could use a Hartree-Fock starting point because there exists a single determinant that is consistent with the configuration and the state. However, and I remind you because last time I talked about this, for the singlet s state of carbon, still 1s squared, 2s squared, 2p squared, there's another state, the singlet s state, that cannot be written down as any single determinant. In the case of the carbon atom, the singlet s state has to be written down as 1s alpha, 1s beta, 2s alpha, 2s beta. That's boring. But then 2pz alpha, 2pz beta, but some mixture of 1s alpha, 1s beta, 2s alpha, 2s beta, 2px alpha, 2px beta, and then another part, 2py alpha, 2. Say, is that really true, Jack? Yeah, it is true. There's no single determinant that you can prove is singlet and has L equals 0 that involves 2p times 2p, double occupancy of the 2p. So in this case, we have, for this configuration, 2p squared, but for the singlet S state, this is the simplest configuration state function that can be written down. It's not a single determinant. We should not use Hartree-Fock theory because it's predicated on a single Slater determinant. So if we wanted to do, this is sort of scary news to many people, if you want to do some calculation where you're breaking the molecule apart and it's going to produce a carbon atom, and you have to do a calculation on the carbon atom, if the carbon's in the ground triplet p state, you're okay. You can use Hartree-Fock theory as your starting point. If the atom somehow is in a singlet S excited state of the carbon atom, you're dead meat. You shouldn't use Hartree-Fock. You have to use techniques that we need to still talk about. So this is an example of where it has nothing really to do with breaking the bond apart. We know that problem with Hartree-Fock with like sigma squared breaking apart into something that's half ionic and half covalent. That's one of the problems of a determinant that has like a sigma squared or pi squared occupancy. Here I'm talking about a different aspect that just as an existing entity, an atom, sometimes the state you're after just cannot be written as a single determinant in its simplest form. There's no single determinant that has the right symmetry is the problem here. So this is another example of where we should not be doing Hartree-Fock theory, just like breaking bonds.